Hello. Today we will discuss the Runga-Kutta method. First, let's review some ideas about improving Euler's method. Recall that we were motivated by the following question. We know that Euler's method gives us a good algorithm of computing an approximate solution to a differential equation. But does there exist another algorithm which gives a better bound on the error? In order to gain some intuition behind how we should improve an Euler's method, recall that we looked at the error coming from Euler's method. The idea is that if y of t is an exact solution to an equation of the form, say dy dt equals f of ty, then we have a Taylor series expansion which says y of t plus h minus y of t minus f of ty times h in absolute value is less than or equal to m sub 1 times h squared for some constant m sub 1. Using this concept, but now staring at the Taylor series in more detail, we can find a different constant such that y of t plus h minus y of t minus the ratio f of ty plus f of t sub h, comma, y sub l, all divided by 2 times h in absolute value is less than or equal to m sub 1 times h cubed, where now L is f of ty times h. Using this, we can then find a different algorithm from Euler's method to find points that are even closer to the actual solution. Our algorithm for the so-called improved Euler's method is as follows. Let's consider an initial value problem, dy dt equals f of ty, where y at t0 equals y0. Fix its step size h and recursively perform the following steps. First, compute a slope m sub k, which is f of tk yk. Second, computer time t sub k plus 1 equals tk plus our step size h. Third, compute the value y tilde at k plus 1, which is yk plus the slope m sub k times the step size h. Fourth, find a new slope n sub k, which is f of tk plus 1, y tilde k plus 1. And finally, compute the new value y sub k plus 1 as y sub k plus the average mk plus nk over 2 times the step size h. This technique is known as the improved Euler's method or the modified Euler's method. Some texts call this Hoyne's method, and yet others call this the second order Rangakata method. There is a geometric interpretation behind all of this. The idea is that Euler's method gives us a so-called Euler's point, which just comes from drawing a line with a slope m sub k. However, the improved Euler's method tries to improve upon this by correcting to a slightly different point. That is, we have instead a different slope, which is just the slope that we had at the Euler point from before. The Hoyne point now just considers the average of these two. That is, essentially, we just want the average of the slopes. In other words, the improved Euler's method is a type of predictor-corrector method. The Euler point is what we predict from Euler's method, but there is a corrector point coming from looking at the slope at this Euler point. Finally, we ask the question, how can we measure the error as it grows as a function of the step size h? The idea is that the error is actually dependent quadratically on the step size h. That is, with a couple of mild conditions on our function f, we can find constants m1 and m2 so that the total error is less than or equal to m1 over m2 times e to the m2 times b minus a minus 1 times h squared. In other words, there is a constant c so that our error is less than or equal to c times h squared. Today, we generalize some of these concepts and look at what's called the Runga-Kutta method. As before, say that we have a one-dimensional system of the form dy dt equals f of ty, where y at t0 equals y0. As we just stated, under some mild conditions on our function f, we can find a unique solution y of t. We've already seen that we can define a sequence of points t sub k, y sub k recursively as follows. The time satisfies t sub k plus 1 equals tk plus a step size delta t. But the value y sub k satisfies y sub k plus 1 equals y sub k plus delta t times one of two possible slopes. Either it's f of tk yk if we're dealing with Euler's method, or it's the average of f of tk and f of tk plus h and yk plus f of tk times delta t for the improved Euler's method. Then, under other mild conditions on our function f, we can find a constant c so that the error is less than or equal to c times h to the e. In this case, e is equal to 1 if we're dealing with Euler's method, and e is equal to 2 if we're dealing with the improved Euler's method. Today, we'll introduce a method where our error would satisfy e equals 4. This is what's called the Rangakata method. Now, instead of considering a one-dimensional system, let's consider our most general case of an n-dimensional system. We'll fix a step size h and perform the following steps. Let's compute the slope k sub 1, which is f at t sub k, y sub k. Second, let's compute the slope k sub 2, which is f of tk plus 1 half h, comma, y sub k plus 1 half h times k sub 1. Third, k sub 3 is f evaluated at tk plus 1 half h, and yk plus 1 half h times k sub 2. Next, we'll compute the slope k sub 4, which is f of tk plus h, and y sub k as plus h times k sub 3. Next, we'll increase the time to consider t sub k plus 1 is t sub k plus h. And finally, we'll compute the value y sub k plus 1 is y sub k plus h times this weighted average, k1 plus twice k2 plus twice k3 plus k4, all divided by 6. Of course, we then return back to step number 1 and replace k with k plus 1. Apply to these points tk, yk will give us an approximate plot of the graph of the actual solution. This is known as the Runge-Kutta method after the German mathematicians Karl Runge and Martin Kutta. There is a geometric interpretation of all of this. Here on the right-hand side of your screen, you can see a diagram of what's actually happening. Let's say that we start at a point tk, yk, which in this case might be represented as t0, y0. We know that we're going to try to go from tk to tk plus 1, so we have a width here along the t-axis of our step size h. First, we can see that at the point t0, y0, we have a slope which we denote as k sub 1. As we move towards the middle of our interval, that is tk plus h over 2, we now have two possible slopes, k sub 2 and k sub 3. K sub 2 would be the slope that we would find coming from the k sub 1 step, but then k sub 3 is what we'd find now by placing in what would happen at the k sub 2 step. You may want to think of this middle part here in terms of k2 and k3 as what happened with the improved Euler method. Finally, at the end of this interval, we have our slope k sub 4. Now, if we take the weighted average of these four slopes, this will give us the point yk plus 1 in terms of y sub k. We give an example of this. Let's consider the initial value problem dy dt equals negative 2t times y squared, where y of 0 equals 1. We can actually find the exact solution to this equation as y of t as 1 over 1 plus t squared. Moreover, we can find an approximate solution just by considering the points tk, yk defined in terms of the Runge-Kutta method as you see here on your screen. Now, numerically, we can work out the numbers to see, in this case, if we have a step size h of 0.125, then we'll have 16 points as t ranges between 0 and 2. We didn't put the error here on this screen just because there wasn't enough space, but you can get an idea of how the error will be computed. What's more important here is to take a look at the various graphs of the actual solutions. The solid blue line is the actual solution. Y of t is 1 over 1 plus t squared. On the left, we have a plot of the dots, that is the approximate solution we would find coming from Euler's method with the step size here of 0.125. On the right-hand side, you can see the dots, that is the approximate solution we would find coming from the Runga-Kutta method, also with the step size of 0.125. You can see that Euler's method gives a reasonable approximation, but the Runge-Kutta method seems to hit the answer almost exactly on the nose. To get a better idea of exactly what we mean here we've taken a look at the solution we would find from the Runge-Kutta method, where our step size is very small. In this case, our step size is 0.001. You can see that we have almost a near perfect reproduction of the actual solution, y of t equals 1 over 1 plus t squared. But what can we say about the actual error that we would find? As before, let's consider a rectangle where t goes between a and b and y goes between c and d. We'll place a few mild conditions on our function f, specifically that the fourth order partial derivatives should all exist and be continuous in this rectangle. Moreover, let's say that we have an approximate solution, that is points tk, yk, coming from the Runge-Kutta method of some step size h. Then we can prove that there exist constants m1 and m2 so that our error is less than or equal to m1 over m2 times e to the m2 times b minus a minus 1 times h to the fourth. In other words, we've now shown that the error satisfies an inequality of the form c times h to the e. In this case, e is equal to 1 when we're dealing with Euler's method, e is equal to 2 when we're dealing with the improved Euler's method, and e is equal to 4 when we're dealing now with the Runge-Kutta method. For this reason, we say that the Runge-Kutta method is a fourth order method, and the improved Euler's method is a second order method. Thanks very much for watching.